Hello. Yeah, we can get going now. Before we stop, just for a break there, I was asked about heat and corrosion, and I think the best example that we could give you right now is if you take a stainless steel pipeline and the passive film inside the pipeline is damaged for whatever reason, the corrosion products, usually chlorides, would attack the hole where the film is broken and then just drill down into the pipeline, and then once it's inside, it will start to eat away at the microstructure of the steel, and it will keep going. It's probably one of the most aggressive and dangerous forms of corrosion because it's not easily detectable until you've got such a large hole that it's basically punctured right through. Okay, so if we move on. So methods to improve the corrosion resistance, and this is what we're going to be talking about now in the next half an hour or so. The external corrosion and internal corrosion. So for external corrosion, to help prevent it, you've got two methods, coatings and cathodic protection. And in internal, you can use coatings or inhibitors, as I mentioned earlier. Just a couple of photographs there to show you different forms of corrosion. Not too sure what's happened here actually, but obviously the pipeline has burst from the outside. Sorry, from the inside. But anyway, this is obviously an offshore platform at the sea level, which we call the splash zone, and obviously I'm not sure what that actually was, but it's obviously been eaten away. And here is another pile for a jacket. It's been corroding away there. So external coatings is the primary defence against external corrosion, cathodic protection being the secondary defence against corrosion. The coating selection is pretty critical. You get different types of coating, which we'll come on to in a little bit. But when selecting your coating, as the slide says, it's important to take into consideration these items. The coating must comply with the manufacturer's data sheets. That's imperative. Mixing, application, curing, all vital. If you get one of these three items wrong, then your coating is doomed right from the very start, especially the surface preparation prior to applying the coating. As it says here, actually, inadequate or incorrect surface preparation is the most common cause for premature failure. And then consider the effect of cathodic protection if applied, and we'll talk about that in a little while. What happens is the cathodic protection, if it's applied, if cathodic protection is applied too aggressively, then it will cause the coating to despond and break away from the pipeline. So this table just gives you a short overview of different types of coatings here. Epoxy or FBE, 3-layer, polypropylene, polyethylene, and foam. Some examples of applications and the temperature limits at which the coatings can be used for. Internal coatings not only act as a defence against corrosion from the inside, but also they aid the flow of the product Terry would have probably mentioned in his presentation recently when we discussed flow assurance. Navigo flow coatings can also be used. Additional primer and thermal insulation. We get two different types of body protection, but sacrificial and impressed. Sacrificial, as the name implies, you place the anodes onto the outside of the pipeline, and the pipeline is obviously the cathode and the anode is the anode, and the anode will sacrifice itself to protect the pipeline. But it's a natural process which happens, and that also depends on the type of electrolyte or water that the pipeline is laying in. The impressed system is driven by a power unit from a transformer rectifier, and you can control that more. Obviously, a sacrificial system you can't control at all. It's just there. There's not much you can do about it. Whereas you can control the voltage from an impressed system. Body protection obviously also reduces the rate of corrosion. If you've got corrosion, that is, it will slow it down and stop it. Would not stop it, but slow it down to a point where the pipeline is operationally safe. And the design is determined by the bare metal area resistance, the environment coating type. So we have a diagram of what's actually happening. The anode here is called a standoff anode, and it's connected to the pipeline by welding is the best method, but sometimes they're bolted onto the pipeline. And there it's showing you what's happening in terms of how the anode is performing to protect the pipeline. Steel, carbon manganese steel has a natural potential of around about minus 500 millivolts when it's just there in the air. And then to cathodically protect carbon steel, we need to bring that voltage down to around about minus 650 millivolts. But it depends on what the environment is the pipeline is in. Typically, aluminium and zinc anodes are used in low resistivity environments, and magnesium anodes high resistivity. Okay, what I'm going to do now is just give you an example of a CP calculation. There's different ways of completing a CP design, usually MathCAD, but Excel, or if you're really brave, then just calculate it. So there's different equations that are used in order to design a CP system. What I'm going to show you here on this MathCAD sheet is a CP design in its entirety. It's too much to go through tonight in the time that we've got. So I'll show you this, and then on the board there I'll just take you through some of the equations. So this is actually a real project that not we, but the company that this is from, I used to work for, and it's for the Shargis Phase 2 development in the just off the coast of Baku, Azerbaijan, as you can see. So as you can see, there's a lot of information here, and it has to take into account the coating, which in this case is a 3-layer polyethylene coating, and CWC stands for concrete weight coat. If Ellie mentioned concrete weight coating in his presentation, to give the pipeline more stability and weight to keep it on the seabed. In case the pipeline is liquid, this also acts as a guard to help protect the pipeline against third-party damage such as anchors and trawling fishing nets. So it's 39 pages here altogether, so I won't go through the whole thing. It'll take too long. The idea is, as I said, really is just to show you what is involved with a CV design. But if you have any questions on what you're looking at, then just shout out and I can stop. So there's the operating conditions.
Is this coming in the exam?
Not to this extent, no. So the actual anode that you're going to be using has a tapered edge. All of this needs to be taken into account in terms of the dimensions. Heat transfer coefficients, pipeline data, diameters, external coatings. So as you can see, it's quite involved, and if any of you have experience of MathCAD, then it's quite easy to calculate once you've got the MathCAD sheet set up. But that obviously takes a lot of time. It's really less environmental data.
Yes.
So there we go, I think that's enough of that really. But that gives you an idea of what's involved when it comes to calculating a CP design. And that would have been for a sacrificial system.
All of that's the exam.
Right. I need my paper because I can't remember the equations off the top of my head. Can everyone see the board okay? You guys over there? Can you see this all right? Sure. You have to excuse my handwriting. Especially all these things I can never write. So when it comes to designing a CP system, what do you think one of the factors is that you need to know when it comes to designing a CP system in terms of anodes?
Design life?
Right.
Design life?
Design life, yep. And I was going to do that in a couple of minutes, but like to determine the
Length of the line?
you already know the length of lines, you've got that, but to determine how to adequately protect the pipeline, you obviously need to know how many, what might be. Sorry? CP units. Do you mean anodes? Yeah. So to determine the number of anodes, you need to know the consumption rate multiplied by the design life you require, which is typically 25 years.
Your dark pen.
Sorry?
Your dark pen.
Dark pen.
I think there's a black pen here. Is that more visible?
Do you want me to rewrite that, or is that okay?
Yeah, that's fine.
Yeah.
And the font size too.
Huh?
The font size.
Font size.
Yes, sir.
Okay, I'll try and write bigger. Utilization factor times by okay, so for the number of anodes that you want, it's the consumption rate times the design life times the current required divided by the utilization factor and the weight per anode. So if you had so in this particular example then, if the weight of the anode was 60 pounds and the current consumption was 0.75 pounds per amp year, design life was 20 years. 15 amps current, and a utilization factor of 0.6. Is to take those inputs and put it into that equation, that would give you 7 anodes.
What do you mean by utilization factor?
Sorry?
Utilization.
Utilization.
What is it?
It's the. Gosh, how do I describe that?
It's the amount of time.
Sorry?
It's the amount that the item is being used.
Yeah. It's to take, if you was to take one anode and that one anode, try and calculate just how much current that anode would require to be used. Yeah.
So it's a single factor.
Pretty much, yeah. But most of these items are tabulated anyway within the specifications and the standards. So you don't actually have to work it out. Okay, so that's one equation you would need Now, if you wanted to work out a long pipeline, and obviously all your anodes are going to be laid across the pipeline horizontally, then you would need White's equation. Your guys, it's a private conversation. Just wait till later. Okay, so for Dwight's equation to work out how many anodes you would require to be placed on a long pipeline in a horizontal fashion, you need to know the resistance in ohms. Rho would be the resistivity ohm centimeters. Length of the pipeline. Yep.
By horizontal setup, you mean a series of pipes parallel to each other, or just a flat pipe in the room?
Just a flat pipe, so if this is your pipeline working along, you would, at the end of this equation, you would have, it would tell you how many anodes you need here, 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 and all the way along the length of the pipeline. So this is the depth of the anode in feet. When I say depth, I mean the depth of the anode itself, not the water depth. And D is the diameter. So if you take that, rho divided by L, log 4 times length squared, plus 4 length again. This will minus square root of S squared plus length squared divided by the length minus 1.
Excuse me. Is the last symbol J? J is equal to 5. D.
On the left.
Last symbol. Here.
Yeah.
D. Sorry, it's my right. Diameter. Diameter of the anode. So all I'm doing here really is just showing you the type of equations that you would have probably noticed in the MathCAD sheet that I had up on the screen a few moments ago. So if you had rho ohm centimeters, if you had 10,000 ohm centimeters, length was 7 foot. The S, was twice the depth in feet, so let's say 12 feet, and the diameter is 0.667. If you just plug these figures into this equation, it will give you.
Is the diameter also in feet?
Sorry?
The diameter. There's a unit for diameter.
Yes, sorry, feet, yeah. just plug those variables into that equation, it should be 22.49 ohms, which you could then put into the, and then once you've got ohms, using Ohm's law, you can work out the amps that are required, and from there, you could put it into that first equation that I showed you a few moments ago, and it'll give you the quantity of amps. Does anybody have any questions on that? No? Okay. So we'll move on now, because what I wanted to do there is just show you just an example of an equation you can use, as I showed you on the MATCAD sheet. Right. That completes the subjects of material selection and corrosion and corrosion protection. So now we're going to move on to welding. And to help me with this particular section, I've got my colleague Richard, who's sitting over here in the white shirt, and he'll speak to you in a little while with regards to some video clips that I'd like to show you. Okay, so welding. As you can see, this is the Eiffel Tower that was being constructed, and this on the right hand side is a platform that's in the North Sea. It's in the Norwegian sector of the North Sea. The concrete legs, the legs that you see there are concrete, reinforced concrete, and that's to scale, so it gives you some idea of just how vast these platforms are. It's going to be great. Welding, going back to the early days, didn't really take off in terms of the use for construction, because back in the early days they used to rivet metal together instead of welding, and at the time they also didn't know much about fracture mechanics and how welding two pieces of metal together, what effect that weld would have on the metal. Obviously, if you've got a piece of metal that's riveted together, the crack propagation won't go very far, because as soon as it reaches the space where the metal is riveted together, the crack will stop. Obviously, if your metal is welded together, the crack will just keep on going. This ship, what's that ship called?
Liberty ship.
And that was taken during the Second World War, roundabouts, yeah. And as you can see, it was one of the first ships that was used, first ships that were built using welding to construct, and it's just broken in half because they didn't have a full understanding of the fracture mechanics behind it. Again, just a couple of platforms there, showing the sort of harsh conditions that these platforms are in. Okay, this photo on the left-hand side is a lay barge. Inside here is just like one big factory where the lengths of pipe, or joints of pipe, as we call them, are brought out to the lay barge, and they're loaded on, and down inside the hull is a welding line using equipment like you see there in the photograph, and then the pipeline comes off the back into the sea, what they call a stinger. To give you some idea of the costs involved, a vessel like this would cost you $1 million a day plus. So it's if you sorry, the hire, yeah.
Why don't the company just budge it on?
It's
because a lot more.
So if if you're laying a pipeline across the North Sea from, say, here to Amsterdam, then it's cheaper to give a contract to All Seas and use one of their vessels than it is for, BP or Shell or whoever to have their own vessel. So, yeah, this is just some of the topics that we're just going to talk about over the next half an hour or so. The definition, obviously, is the joining of metal, reducing sealants of material through the heating of the suit to a suitable temperature, with or without pressure, with or without a filament. Three important parameters are required to be taken into consideration when you're welding: the heat input, the speed at which you weld, and machining. Obviously, if you don't have the right temperature, and if you don't have the right temperature and the right speed, then you're not going to be able to create a good weld. Just give you some idea of the temperatures involved here with welding. To create a plasma arc, as it says there, 20,000 degrees centigrade, which is 3 times the temperature of the sun. And to put that into perspective, when you smoke a cigarette will burn at approximately 300 degrees, and your lighter is about 1,500 degrees. The melting point for steel, by the way, is also around about 1,500 degrees. And so there you go, you've got a welder, he's got his welding torch, 20,000 degrees. He needs to know what he's doing. There are the photographs. This is actually a rather poor example of a Rich, help me, what's the word?
It's like it's a welding machine.
Yeah, welding machine. It's not very good condition. And there you've got the tip of the welding torch melting down, and a picture of the sun on the right hand side. Some more interesting photographs for you. Obviously, health and safety is pretty important when you're welding, but depending on what part of the weld you go to, you'll see all sorts of bizarre things. This guy wearing flip-flops, smoking a cigarette, and he's holding the item he's welding with his hand. This is also another welding unit. You know, inside a transformer it's made of plates. And there they've got the plates, and they've just held them together with string. Some more good examples of a welding mask, sunglasses, and a piece of cloth, I guess. And then some of the best welders ever. Billy Connolly used to be a welder before he became a comedian, and filmed flash dance. Now, welding doesn't just have to be what's my thread? Welding, a lot of people associate welding with taking your car to the garage and it's failed its MOT because the bottom seal by the door is rusty, and then the mechanic gets out his welding machine and a bit of plate and bangs it over, and then welds around, and everyone thinks that that's fine and it's all well and good. But obviously you get different types of welding, and the type of welding that we're involved with is terribly complex and terribly and very difficult, as well as a lot of things that you have to take into consideration. Some people think that you can't weld under the sea, but if you can, there's a picture of a diver welding. Just think of all of that current electricity ultimately links to that. You can weld. Welding in space, and this top photo on the right hand side is Russian trying to think of word really, but what they're doing is they've got a huge transformer, probably about half the size of this room, and they build up the current in this thing, and then they just let it go, and goes into the metal, and then they push the two ends of the pipe together and just fuse it together. Not a very safe thing to do, and it's not very practical either. Submerged arc welding is one of the methods, and as it says, metal joined by fusing an electric arc struck between bare metal and the electrode. Would be a weld that we have on the end of this stick. Now, metallurgists don't like welders because a metallurgist, when he's designing a pipeline, he select the materials going to be used, and microstructure, the grain boundaries within the steel are going to be just perfect. And then along come the welders, join it together. Obviously, the heat that's involved in making that weld affects the microstructure of the steel, because it turns everything upside down and causing problems. There we go, some more pictures of sub-arc welding. This is actually in a pipe mill using a welding machine. Rich, can you explain a bit about the process there?
Yeah, sure. Yeah, they've got, so they've got a plate of metal and they've gone and wrapped it up into a pipe. We've got where it joins at the top, we've got a seam. And to close up the seam is running a length along the pipe. So this is submerged because they are submerged under the flux powder granules. And it's actually, this is a complex machine with 3 wires coming down here. And each one's got an electric arc struck off, and it's all hidden under this blanket of metal here. Under the flux here. And you've got melting and a nice controlled pool of metal there that is melting a bit into the plate metal. And as the welding head progresses along, obviously the temperature decreases behind and the metal solidifies. And what with the control of the chemistry of the 3 wires coming in, with the control of the chemistry of the flux, you get the right chemistry of the metal. It solidifies with a beautiful structure which has good strength, and in actual fact the weld is at least as strong as the pipe itself, and it can take the full pressure that the pipe, the metal alone, could take, and you do that all day every day, making large diameter pipes. But obviously this is a very automated setup. And this process, unfortunately, because you can only use it down, because that's a very high power, high current process. In any other position, gravity would make the metal fall away. So a beautiful high productivity process, but limited to factories, unfortunately. So,
Top photo there is a vessel. Again, that gives you some idea of the size of these things. You can see the guy standing there as well. And these type of vessels are not only found in refineries, but also on offshore platforms themselves. This here is the powder that you see on top there. When the weld is complete, this powder should just fall off. It looks like an eggshell, you know. That would indicate that the weld is good. If you get problems trying to take this powder off, you know you've probably got a bad weld. Manual metal arc welding, again, it's just a different method. Conventional and struck between the weld and the consumable rod. The cellulosic welding rods, we've bought some here for you to have a look at. No, we haven't actually, have we?
I forgot to bring the one that's open on the wall of the office, but unfortunately all I can show you is a can. These are actually used by pipe welders, but I'm loath to open them because they cost 70 quid and it's sealed up with this pull thing to keep the moisture in, to give it a sky-high hydrogen level. I've got an open tin at home, so I'm loath to open 70 quid's worth and let the slab start drying. So I'm sorry. But yes, I forgot to bring the open ones.
Bring them next week.
Some of the advantages of this welding is that it's very versatile, reliability is very high, the welders required to do it require a high level of skill, and the equipment is relatively cheap. This is one of the rods that's in that tin, and there you see the cap that you saw back in one of the earlier photographs. And again, just another picture of the welder.
New message from Call Alert.
If anyone were interested, you've got in that process you've just seen, you've got a steel wire, steel rod, and it's covered with a mineral, which when you burn the arc here, you've got both metal dripping away here, melting away and going across, and you've got the flux melting and dropping across. So just like a submerged arc weld in the pipe mill, you're desiring to have both metal and molten slag. But here you're achieving on a much smaller scale that a person can actually manually manipulate.
There you've got different types, manual with the man that you saw in the photograph before, mechanised, and of course nowadays there's a lot of robots involved with welding. Again, you've got high productivity, versatility is good, but it can be quite high tech. The preparation that you require for welding is also equally as important, probably just as important as preparing the surface of the pipeline before you coat it. The preparation, the weld bevel at the ends needs to be free of grease and contaminants. You need to have it lined up perfectly. To aid you with lining the pipeline up, there's a device that goes, I don't think I've got a picture of it actually, but it's like a pig that goes down inside the pipeline and it will stop, and it's like a plug basically that will hold the pipeline together and hold it true in line, so that when they weld around the top, and you're not going to get any mismatch, or if there is mismatch, it's going to be very, very minimal. And again, things like mismatch, etc., can obviously affect the integrity of the weld, strength, etc. Preheating of the workpiece before you weld. The pipeline is heated up, preferably with induction coils. But obviously, sometimes if you're welding out in the field in the middle of the countryside, if it's an onshore pipeline, then you don't always have induction heaters, so you use blow torches. Blow torches have its own inherent problems when it comes to coating the pipeline afterwards. The sequence of the weld, root pass, hot pass, fill passes, and then cap pass. And basically what you're doing is your pipeline is held together with the clamp. The clamp goes down inside the middle. Then the first pass is the root pass that essentially hold it together, make it more permanent, and then we go over it again and then again until we've welded up. Sometimes you need quite a few passes. For a large 32-inch diameter pipeline, you can take, Rich, how long could it take to build a 32-inch diameter?
I think the fastest is something like 10 minutes now, but it would take hours for one person.
Yeah,
To do.
one person.
Yeah. So it's with a machine with many welding heads working simultaneously. It can use 10 minutes.
Same with ball joins, potential weak spots. Under matching, as I just mentioned a little while ago, under matching will be achieved depending on the strength. And consequently, that makes a weak joint. Matching is when the weld has similar strength to the base metal, and that obviously will make sure that the weld is strong.
In case they're asking, this is just for if I'm asked later about MIG torches.
Oh, okay, right. When you're welding two pieces of pipe together, the heat is obviously going to spread through the pipeline, heat transfer through the pipeline. That's called the heat affected zone. It's enough to change the microstructure of the steel, and that can have all sorts of consequences on corrosion, perforation, weld corrosion, and also the strength of the pipeline as well. So if you're changing grain boundaries and the microstructure of the pipeline become more brittle, can become more brittle, and eventually leads to weld failure. Some of the welding defects that you can get, lack of fusion, penetration, cracks, incorrect shape, size and porosity. So I'll show you what porosity looks like in a few moments. There's service defects that can arise as a result of bad welding, brittle fracture, as I said, the pipeline probably more brittle, stress corrosion cracking, as you saw in the video earlier on, mentioned a couple of times, and fatigue failure. The stress cracking can also be induced by hydrogen. It's another byproduct of welding. You're going to, when you weld the pipeline together, you introduce hydrogen into the metal, and that can lead to hydrogen-induced stress cracking. Again, disasters. I said that there's been many before, and there's been some recently since that video you saw earlier. This platform was back in the 70s, I believe. What happened was one of the support members between the legs, the weld failed, causing the leg to collapse as it couldn't take the weight, and that's what happened. The picture you see at the top right-hand corner is from the Welding Institute, and it's the weld of this actual failure. You probably can't see the lighting there. So, this is the support. I can't read that either.
Hydrophone support
Yeah.
tube.
Then at the top there you've got the interior of the brace. Figures indicate service life in months. Okay, without the supporting notes, I can't talk too much more about There's a couple of examples of welding defects. You've got porosity